right. So we finished up last time. Well, we had made our way through an example. We were talking about some hypothesis testing stuff, right? And so just to get us all back on track, what we had done is we said we've got a group of investigators who feel like or believe that antioxidant supplements could help improve cognitive decline in older adults. So what we do is we have 25 adults, 65 and over, take supplements for a period of 6 months. Okay, and what we do is we then, once that's done, we give them a neurological test with a known mean and standard deviation. So this is well standardized, right? So this test has a mean of 80, standard deviation of 20 in the general population of older adults, right? And what we see is that previous psychometric research suggests any change or difference that exceeds 10 or more points holds some practical relevance, okay? And so what we want to do is we want to run through a very, very simple single sample hypotheses test because what we want to know is whether or not we have evidence from this data to start to think that perhaps antioxidants may have a beneficial impact on sort of cognitive abilities in older adults, okay? So is everybody with me on the example? Remember, this is kind of what we're doing. Okay. Okay, I kind of like that. That gets me everybody. No, that doesn't give me everybody. I'm sorry, I'm fooling around with... Is that big enough for everybody to see still all right on their screens? Okay, cool. What I like is right now, and you'll see this if you later watch this from my viewpoint, I've got all of you on the same screen so they don't have to flip through and target whoever happens to be in my line of sight at any given point. Now you're all in my line of sight, so I can target any of you at whim. All right, so first thing what we're going to do is we're going to go through, we need to state our hypotheses, right? We've got our null hypotheses, our alternative hypotheses. Remember that our hypotheses are always stated with reference to a population, right? We don't care about the sample. Sample is just a mean to an end, or a means to an end. I can't access the population. I can't directly measure the population. But what I can do is I can pull samples and then make inferences about the population. So if I say there's a zero association between the IV and the DV in the larger population, or I'm saying the manipulation has no effect on outcome, what I'm saying is in sort of the general population, X and Y aren't related. There's no association going on. My groups aren't different. But I don't care about differences in the sample. I'm never going to say this. My null hypothesis is that my samples aren't different. Because, Riley, will my samples ever be exactly the same? No. So I don't need to pose a hypothesis or run any type of test. I just look at them and say, is this number the same as that number? And if the answer is no, then I'm good. I don't have to do anything fancy, right? But what we're trying to do is we're trying to make a determination, is any difference that we're seeing in this across my two samples big enough to start to assume that there's an association under the assumption of the null hypotheses. So null hypotheses, alternative hypotheses, both always about the population. Null hypotheses saying there's no impact, there's nothing going on. Alternative hypotheses saying that groups are different, things are related, things along those lines. Okay. In our hypotheses testing, our traditional null hypothesis significant testing, only looking at the null hypotheses. Okay, this is the only thing that we're testing throughout this whole thing. We're going to make inferences about the alternate based on the results of our test, but we're not directly testing the alternate hypotheses. Okay. Talked about not only are we sort of our test of our null hypotheses isn't just an assumption or a test of sort of the actual null hypotheses. We're also testing a lot of other implicit assumptions, auxiliary hypotheses. That my test assumes that my sample is random, or that my sample is representative, that my sample is randomly selected, that all of my numbers are doing the right things that they should be doing based on my statistical test, my measures are valid. If I fail to reject the null hypotheses, it might mean that I have evidence of differences in populations, or it could just mean I have cruddy methods. I don't know. My test doesn't tell me. So again, always needing to make sure that anytime we're looking at stats or research, that we're also taking a close look at our methods as well. Okay. So for our sample here, our null hypothesis is that the mean cognitive functioning score in older adults using herbal supplements is equal to 80, right? Rachel, where did I get that 80 number?
So that's I think it's the general population.
Yeah, the general population. And so essentially what I'm saying is is the population of older adults who take supplements. They're a different population than the general population of older adults. They're their own unique population. But what my null hypothesis is saying is that those older adults who take supplements, their average memory score is the same as everybody else's. There's no difference. Okay. My alternative hypothesis says that average cognitive functioning in the population of older individuals taking herbalist supplements is not equal to 80. Right. I'm not saying it's sort of which way it is. I have some based on the study, I have some guesses to which way it's going. But I'm just saying that older adults who take herbal supplements, they're a different population. No one's disputing that. But I'm also saying that they have a different average cognitive functioning score than sort of general older adults in general. Okay. So I'm going to go through, set up my decision criterion. And our decision criterion is, so the logic behind this is we say, assuming that the null hypothesis is true, okay? Assuming that older adults who take cognitive supplements do have a mean score of 80. How far away from that? How far away from that score do I need to get a sample before I start to question the validity of that null hypothesis, okay? And so, if I go through and I say, under my null hypothesis, I assume that the average functioning score for older adults who use supplements is 80. Okay. Now, if I pull a sample of older adults who use supplements and I get a score that's close to 80, Ari, what is my conclusion? Yeah. So let's say that under the null hypothesis, I'm assuming that the average cognitive functioning score in older adults taking supplements is 80. And let's say I pull a sample and I get a number, an average functioning score that's pretty close to 80. What is my conclusion?
That it is correct. That the null is correct.
Okay, cool. Not quite, but again, I'm glad you. No. This is your answers that are just a little bit off are more helpful and informative than stuff that's spot on, right? We would never say, and never ever, that we would say that this data proves the null hypothesis. We can never prove the null hypothesis. We can't say that the null hypothesis is true, right? What we can say is that the null hypothesis is plausible based on these data, right? So if I say the average functioning score in older adults who take supplements is 80, and then I sample some older adults who take supplements, and that score is pretty close to 80, then I'm going to say the null seems to be reasonable. Like, these data are reasonable given the null hypothesis. Given the null hypothesis, these data are not unexpected. And so as a consequence, we would say, I'm not saying the null hypothesis is true. I'm just saying that I can't say that it's not. I don't have evidence to say that it's not, right? So that would be if we get something that's very close to sort of that 80 point. Erica, what happens if I don't get something close to 80? What if I get something that's very, very different than 80?
Then the null is most likely not true.
Yeah, right. What we would do is we would take that as evidence against the null hypothesis, right? Now, if the average functioning score in older adults who use supplements is 80, is it very likely or unlikely, assuming I've got a big sample, that I get at, say, a sample of adults of 100 who have an average cognitive score of 90 instead of 80? Would that be a common thing that I would get if the true population score is 80? Erica?
Sorry, could you repeat that?
Yeah. So let's say if I assume that, and I got a big sample, good representative sample, right? And I'm assuming that the real score that I can't see, but the real functioning score of older adults taking supplements is actually 80. But I go through and I get a good sample of older adults who take supplements, and their score is 90, right? Is that something that I would expect, or is that something that's expected or very unexpected?
Compared to the null, I would say it's unexpected.
It's unexpected, right? And so assuming that the null hypothesis is true, it would be very, very unlikely for me to obtain the data that I've gotten, right? If the actual average functioning score in older adults taking supplements is 80, and I get a good random sample, and I sort of that's reasonably large, and I find that they have an average score of 90, I would say that these data aren't compatible with the null hypotheses. It seems like these data are likely drawn from a population that has some score that's not 80. My best guess is 90. It's just not, but I'm going to have some confidence bounds around there. It just doesn't appear to be pulled from a population with 80, right? And so what I would then do is use that as evidence against the null hypothesis and conclude that older adults who take supplements likely have higher cognitive scores than the general population of older adults. Okay, so again, what this is all about is saying, here's my null hypothesis. This is what I expect as a baseline. And what I'm going to do is I'm going to collect some data, and if that null hypothesis is true, I should expect something that sort of falls in close to that. But if I get something that deviates quite far and my methods are good, and I haven't violated or grossly misspecified the model or screwed around with any other stuff like that, and I still get something that's very different, I'm going to take that as evidence that the characteristics of this population I'm interested in are different in some systematic way than sort of whatever's presented under my null. Okay. Sort of get this, sort of understand kind of what's going on. Okay. So, again, remember that if I have data that's incompatible with either my null or the assumptions of the model, right? I could have problems with how I've gone through and sort of calculated things, or sort of my statistic I've calculated doesn't follow the distribution that I expect it to, right? And so I would say that that's evidence against the null hypothesis. But if the sample data are consistent or similar to whatever my hypothesized parameter is under the null, then I'm going to say it's close, right? I'm not going to say that that data means that the null is true, right? I'm just saying that it's not incompatible with what we would expect given the null hypotheses. Okay. And so this threshold for what we determine for statistical significance in a traditional sense, this is determined by you all, right? You get to say how far away, what's the probability function, like how unlikely do these data need to be, assuming that the null hypothesis is true, before I start to sort of conclude that these data are likely incompatible with the null hypothesis, suggesting that my sample of or my population of interest has some different characteristic or something along these lines. Okay, and this is set by your alpha level. So again, if we're going through and plotting this out in a traditional Z-curve, what we've got is a critical region out here in the tails, set by our alpha levels. This if I get something out here, Allie, what is my conclusion, or what am I starting to conclude?
If you get something in the critical regions, then it's probably something that's a little bit more like unlikely or like significant.
Yeah, right. We would say that these data are unlikely, assuming that the null hypothesis is true. Assuming that older adults taking supplements have a mean score of 80, the likelihood of us obtaining a random sample with these characteristics is rare, right? Suggesting that then maybe the older adults taking supplements don't actually have a mean score of 80, right? But what about stuff if I fall in the body of the curve here, Allie? What am I assuming then?
It's pretty normal or likely to happen.
Yeah, it's at least not surprising, right? The data that we've got appear to be relatively consistent with whatever characteristics of the population we're assuming under the null. Okay. Now, again, this is assuming that we've run a perfect study, that we haven't violated any of our other sort of basic assumptions. It assumes that we've picked the right test, that we don't have weird data stuff, that our methods are all good. But if we're comfortable with all that, we would say things falling out in the critical region, these are implausible given the data. Right? These are not likely samples to have been drawn from a population with a mean of 80. Is it impossible? What do you think, Robert? Is it impossible for me? Let's say the population of older adults with cognitive who take supplements. Let's say that population does have a mean test score of 80. Is it impossible for me to get something way out here in the tails?
No, it's not impossible.
It's not impossible. It's improbable, right? I could have gotten just a weird score. It could just be a weird thing, right? Maybe the actual population value is 80, and I just managed to get a strange sample that had a score of 95, but it's not likely, right? And that's what we're starting to do, is sort of gauge evidence against the null hypotheses. Okay. So what we're going to do is we're going to go through and we're going to calculate our statistics. Here, if we have a situation where we're comparing some group, some population with unknown parameters against a population with known mean and standard deviation, we can calculate our confidence interval, which we've done. We can also calculate our test statistic. This is our z statistic to calculate, sort of establish that p-value. Again, our z-test, pretty easy, straightforward. We're just taking the mean of our sample minus the assumed mean under the null, and we're dividing it over our standard error. Allie, can you tell me what a standard error is?
It's like the standard deviation of like a bunch of samples that you've taken together.
Yeah. My sampling distribution, right? My standard error is across replications of sample size something, how much would I expect those to jump around, right? And so what we're doing with this test is we're saying, what's the difference that I'm observing in this sample? I'm dividing it by the amount of differences I would expect just due to random variation. And if my difference that I observe is much greater than the difference I would expect due from just random jumping around, what is likely my conclusion?
That you found a likely difference or something.
Right. I'm likely going to say, okay, it seems like these data are unlikely given the null hypotheses, right? Or these data tend to appear to be inconsistent with assumptions, the assumed mean under the null, right? Now, if Natalie, what I observe kind of falls in what I would expect just due to basic random jumping around, what would be my conclusion then?
It would be unlikely that the alternative hypothesis is true.
Okay.
Or maybe not true is the right word, but
okay.
It's likely that the blanking on the words, but like that's all I got. Unlikely that alternative hypothesis is true.
Real quick, do you ever test the alternative hypotheses?
No. I'm blanking on the word of the other hypothesis.
The null.
That's why the null. There we go. It's likely that the null hypothesis is true.
Okay. And again, watch out for that. What we would say is we never say the null hypothesis is true. That should never come out of our mouths, right? We're not ever saying that we have evidence for the null hypothesis. I mean, there's some things that we can do in terms of testing it, but it's sort of a different sort of methodological approach. With our general tests, we just say that we don't have evidence to say to disconfirm this. Right? I'm not saying that the average score in the population of older individuals taking supplements is 80. I'm just saying that I don't have enough evidence to say that it's not. Right? And it starts to become an important difference as we're going through and inferring things, and you'll see why it starts to become important not to take null results as evidence for the null hypothesis.
Can I ask you a question real quick?
Yeah.
Is it just coincidence that the alpha level is 0.05, or is that the same as a p-value?
Okay, we're going to get into that in just a moment. Okay?
Okay, no problem.
Okay. All right. Other questions? All right. So, going to take this and pull this together in our supplement example. Okay. So we've got a couple scenarios. One, say what is the Z statistic if individuals taking antioxidant supplements? Okay. My sample at 25 scored an average of 92 points on the neurological assessment, assuming known mean and standard deviation of this test of 80 as mean, standard deviation of 20. Okay. So I go through, I run my test. I've got 25 older individuals who've been taking antioxidant supplements for 6 months. They take my evaluation and they end up with an average score of 92. Okay. Basically, sort of pretty quick and easy. So I've got a mean of score of 92. Go through, calculate my standard error here. This is just going to be my standard deviation divided by the square root of my sample size here, which gives me a standard error of 4. Okay. Erica, can you tell me, give me a practical interpretation or a conceptual interpretation of that standard error?
Is it like if there were another test that is not far from the mean, or like no?
Yeah. You're on the right track. Can someone help her out?
What did you ask? What does the standard error mean?
Yeah. So we got a standard error of 4. What does that mean?
It means that, yeah, God, I should have just kept quiet.
No, everybody else left Eric out to dry. They just let you hang in there.
Girlfriend. No, I know what standard error is. It's what Allie said. So just how far your mean can deviate from. I don't know. I know what it is. I don't know how to interpret it right now. Does anybody else know?
Isn't it just the? Sorry, was someone speaking?
No, it's all you.
Okay, well, isn't it the same as the standard deviation, but it's for a sample of means instead of?
Yeah. There we go. Perfect, Riley. Exactly. So what this is, if I'm looking at these data, I'm saying that for a sample of 25, assuming that the population has a standard deviation of 20 in terms of scores on this test, I'm saying that I would expect across repeated samples of size 25, I would expect the means of those samples on average to sort of jump around about 4 points. Okay. Above below 80. Now obviously that's on average. You can get samples that are all over the place, right? But I'm saying the standard deviation of the sampling distribution for n equals 25 is about 4. Okay. So if I go through and then calculate my z-score, so I've got 92, my observed value of my sample, minus 80. This is my null, my assumed value under the mean, divided by my standard error of 4. I get a test statistic of 3. Okay, so I have a z-score of 3. And then If I go through and calculate my 95% confidence interval, I've got my mean value of 92 plus or minus 1.96. That's my sort of the z-score associated with my confidence or my level of estimation multiplied by my standard error is 4, gives me a confidence interval of 84.2 on the low end and 99.8 on the high end. Robert, can you give me a practical interpretation of that confidence interval?
That's the plausible, or that's the range of plausible values that we would expect to find in our study to a 95% confidence.
Okay, cool. I think that's good. Scratch the 95% confidence. No one cares about the 95% confidence. If you're trying to wrap the 95% confidence in there, you're going to get kind of turned around, right? But you're exactly right. What I would say is based on these data, I would say that, Robert, what's my best guess of the actual mean cognitive score for older adults taking supplements based on the data that I've collected?
Based on the data you collected, it's 92.
Based on the data I've collected, it's 92. Am I 100% certain that it's actually 92, that that's the actual real population value? No, it's almost certainly not 92, right? But what I'm going to say is the data that I've collected would be consistent with population values ranging anywhere from about 84 to about 100, right? What do you think about that confidence interval, Robert?
What?
84 to 100. How precise is that interval?
I'd say that's pretty good.
You like it? I'd be a little concerned by it. So if it's anywhere from 84 to 100, right? Again, think about like say, I think you're like, average IQ score is anywhere from 85 to 100, right? I'd be like, yikes, that's quite a bit of range there, right? So now we don't know what this test is or kind of what it's doing, but
is that where the context would play a part?
Yeah, a lot of context would start to come into this. But what's our sample size, Robert?
25.
Do we get super precise estimates with 25? No, right? So just knowing sort of sample size can start to give you a general ballpark of whether or not this is going to be a very sort of precise sample, okay? But one more question, Robert. We know that in the general population of older adults, mean performance is 80. Is that a plausible value based on the data that you've collected here?
No.
Okay. So do we need to actually even go through and calculate p-values or any other such thing with this?
No, because it wouldn't show anything.
Yeah. I mean, we will do it, right? And you'll be doing a lot of that. But we don't need to. It's not really giving us that much information above and beyond what we've already calculated here. Okay. All right. So that was one scenario, but rewind, new scenario, alternate universe, new situation going on. Okay. And let's say that I went through and I got a sample of 25 older individuals, and this time they scored an average of 84 on this assessment. Okay. Again, I can just rerun this, right? Rachel, does my standard error change? No, right? Same stuff is going into my standard error. Because this is a z-test, I'm working with the population standard deviation. My sample is still 25, so my standard error is still 4, right? But this time I've got a smaller deviation between what I've observed and so what my expected value is under the mean, right? Before I had a difference of 12 points. Now I've only got a difference of 4 points. If I take 84 minus 80 over 4, I get a z value of 1. And if I go through and I calculate my confidence interval here, I get a confidence bound of about 76 to about 92. So Rachel, can you give me an interpretation of this confidence interval here?
All right, so some plausible values given the data that you have of the true population mean might be between 76.2 and 91.8.
Gorgeous. Absolutely, right? If I said, so based on your data, what is your best guess as to the true mean score in older adults taking supplements?
Your best guess
Yeah,
would be 84.
84. That's my best guess, right? But if I said, Rachel, I don't think it's 84. I think it's more like 78. What would you say?
You could be right.
Yeah, sure, maybe, dude. I don't know. Could be. That's not what I estimated it at, but yeah, that's within the bounds, right? That could be a reasonable estimate based on what we have here. Okay. So what happened? So why are we getting sort of in one situation? So I guess one last thing, Rachel. If I said that the actual score for older adults taking supplements is 80, what would you say?
I'd say that it could be 80. It's within the
Yeah.
confidence interval.
Right. That would be a reasonable estimate based on the data that we've collected, right? Which again, and so when we eventually go and calculate our p values and things like that, are we going to reject the null hypotheses here? No, we're not, right? Because the data that we've collected are reasonable given the null hypotheses. Right? So in scenario 1, where we have a mean value of 92, my alpha level is 0.05, my critical values 1.96. Ari, where did I get 1.96 for my critical values? Okay, it's kind of related to the confidence interval. Where did I get that 1.96 score? Anybody? What were you going to say?
I was looking at the wrong problem, and then I see that it's in the other top problem that we were. I'm just confused myself.
Okay, someone help me out. Where do we get this critical value?
The z-score that's associated with the 95%
Yep.
confidence interval.
Exactly. Nice work, Robert. That's just my z-score associated with a two-tailed test at alpha equal 0.05, right? 1.96. Robert, what percentage of the curve is in the tail at positive 1.96?
2.5%.
0.025, right? And so what this is doing is it's just going through and saying I've got 0.25 or 2.5% here, 2.5% here, and here's my confidence bound. Here's my z-score of 3. Brittany, where does this fall?
In the critical regions, is that what it?
Yep.
Critical region, yeah.
Yep, it's in my critical region out here, right? It's exceeded my critical value, so I've got it out here. And so what is my, Brittany, what is my conclusion based on sort of this test?
Well, are you asking about like the null hypothesis?
Sure, yeah.
That it's improbable.
Yeah, I would say that these data are improbable given the null hypotheses, right? Assuming that older adults who take cognitive supplements do have an average test score of 80, these data would be very unlikely. And how unlikely? This is where we go through and get our p-value. Again, you see I got a little link down here. Online calculators are fantastic, right? If I go 1.96, I compute, right? It gives, not 1.96, 3. I have a test score of 3. Compute my p-value, 0.0027. Okay, and so I would in conventional, sort of round that to 3 decimal places, say give that a p-value of 0.003. And if my alpha level is 0.05, my p-value is 0.003, I would reject the null hypothesis. Okay. All right. In scenario 2, this is where I've got a mean score of 84. Again, alpha level 0.05. Critical values, again, 1.96. Erica, why is my critical value 1.96 still? Completely different problem. Why is it 1.96?
It's still the confidence interval for 95%.
Okay, so good. Love that you're thinking confidence intervals. That's fantastic. Here, this is our critical region for our type 1 error, right? And so if we're using z-tests, it's always going to be 1.96 if we're got it at the alpha 0.05 level, right? But this time I'm going to go through, calculate my confidence interval here. And this time, if I've got a z-score, I've got a z-score of 1, where does this fall, Erica, relative to my critical values?
Within the expected region.
It's in the expected region. And if I go through and I say, what's the p-value for a two-tailed test associated with z equal 1? It's 0.317, and bring us home, Erica, what would I conclude then based on these data?
That with this data, you can't reject the null hypothesis.
Fantastic, right? I'm not saying that the null hypothesis is true. I'm not saying that older adults who take cognitive supplements do have a mean score of 80. I'm just saying that my data that I have aren't sufficient to say that it's not, right? Natalie, what do my data say the mean test score for older adults using cognitive supplements might be? Okay, it's 84, right? But what based on the data, what are values that would be sort of consistent with the data that I've collected?
Anywhere between 76.2 and 91.
Fantastic. Nope. Yeah, no. You're 100% on, right? So what we're saying, Eric is saying, right? If Eric is taking a traditional null hypothesis approach, Erica is saying that I don't have sufficient evidence to say that it's not 80, right? 80 is a reason. I failed to reject the null hypothesis. I don't have evidence I don't have sufficient evidence to claim that older adults taking cognitive supplements don't have a mean score of 80, right? But who feels super good about that? I don't, right? I'm like, well, fine, you don't have enough evidence to say that it's not 80. Well, what is it, right? Like, tell me, like, because I would kind of like to know, right? If I'm invested in supplements and things along those lines, right? But if Natalie's using, sorry to pitch you two against one another, but if Natalie's using confidence intervals, right? Natalie's not just saying, oh, it's not 80, right? That's not super helpful. Natalie can say, well, based on the data I've collected, it's likely be things that would be supported by the data anywhere from about 72.6 to 91.8, right? That's a lot more useful information than just saying that it's not some value, right? And so this is where, if we start to use interval estimation carefully, it starts to tell us a lot more about sort of our data and sort of what to expect out of populations. Questions on this? All right. Let's do this. Let's take a break. Why don't we come back? We'll take 9 minutes. Come back at 3. Let's take 3:27, and we'll take 10, and come back, and we'll jump back into this stuff. Sound good? All right, cool. So, questions about anything that we've covered up to this point? Okay, cool. So, quick detour for a moment on two-tailed versus one-tailed tests. Okay, most of the stuff that you're going to be doing over the course of your research is going to involve two-tailed tests. This is a non-directional test. Okay, so if I say, like, I'm comfortable saying that there is a 5% chance sort of that these data were sort of out there and sort of like they're real, they're samples that were pulled from a population having a value that's equal to the null, but it's just they're really rare samples that are coming off, and I'm saying I'm okay 5% of the time making a type 1 error, right? And a type 1 error says I'm claiming that there's an effect there when there's actually not, right? But if we have a non-directional test, what we need to do is we have to go through and split that up. So if I say my tolerance for a type 1 error is 0.05, what I need to do is I'm going to go through and I'll put 2.5% of that in the upper tail, 2.5% in the lower tail. And so what I need to do is then I need to go through and sort of account for if I miss high or miss low, I'm sort of covering my bases there. Right? So this is a non-directional test, and what I would do then is multiply my probability value by 2 to account for the possibility that I could get it in either tail. So let's say, for example, that I have a z-value of 3. Like we did in our example here, right? We would say that if I get a z-value of 3, and it was 3 above the mean, right? Okay, remember this? What I'm saying is, so if I go through and I find the proportion of the probability in the tail that extends beyond this 3 point, I'm going to find that my proportion in the tail is 0.0013. Okay. But, Rachel, what was my p-value that I calculated here?
0.003.
0.003, right? So if I grab my handy-dandy calculator and I take 0.0013 and I multiply it by 2, I get 0.0026, which gives me 0.03, okay? Because what I'm doing is I'm accounting for the fact that if I were to have found that older adults were to score 12 points below the expected mean down here and I would have got a negative z-score, would I have said, I guess I didn't find anything? No, I still would have claimed that that was a difference too, right? So with our two-tailed tests, what we're doing is we're taking that probability value that would be associated with obtaining a z-score of 3 or higher of 0.0013, and then I'm multiplying that by 2 to get my p-value, okay? But we can also set up one-tailed tests, okay? And if I'm setting up a one-tailed test, I'm putting all my eggs in one basket. I'm saying that I don't care how much lower my sample falls relative to the null. I'm saying it's going to be 100. It's going to be higher, or I'm not going to interpret anything, right? So I don't care if it was 50. I would not interpret that as anything meaningful. I'm only pointing in the sort of in the one direction. And so what we do then with a one-tailed test is we put our critical region all in the upper or lower tail of the distribution, okay? So I'm saying that I'm confident that supplements are going to improve memory. And so if my alpha level is 0.05, I'm putting all that 0.05 in the upper tail, okay? And if I do that, what's going to happen is if I look at, so I'm looking at this in my Z table, I'm looking at the smaller portion here, and I'm going to find something that's close to 0.05 in the upper direction, right? And what I find here is, we'll call it 1.65, okay? And so now that's my new critical value. Because if anything falls on the low end of the distribution, I don't care about it. I'm saying putting all my eggs in one basket, putting it up in the top. So then if my alpha level, if my tolerance for type 1 error is 0.05, I don't have to split it because I'm putting it all on one end. Okay. And so if I do that, it changes my critical value, and is pretty easy to do in terms of tests. The problem, though, is that in calculating my confidence intervals, right? Because my confidence interval has an upper and lower bound, right? And if I want to say I'm just only going to look at sort of the upper bound worth of things, what I need to do is I can't just calculate a confidence interval like I normally would, because that's going to take half in the top, half in the bottom. And so what we do is we typically see people go through, if they're doing a one-directional test and want to calculate a confidence interval, and my alpha is 0.05, what I'm going to do is I'm going to calculate a 90% confidence interval, and then I'm just going to worry about one tail. Okay? Because if it's in the opposite direction, who cares? It's not even going to be a thing that's a concern. And so I'm going to do that, calculate a 90% confidence interval specifically so that all of my alpha level, all of my type 1 error tolerances is going up on the upper end. Okay. So if I'm running a one-tailed test, again, my alpha is still 0.05, but now my critical value is 1.65. Okay. Instead of having 2.5% here and 2.5% here, I'm putting all 0.05 in the top end. And so I still have a value of 92, z-score of 3. But what I've done here is calculated a 90% confidence interval with my lower bound of 85.4 instead of sort of what it was sort of in the previous one. Okay. Because I'm putting all my alpha in one tail. Same thing here, scenario 2. Alpha level is the same, but my critical value has changed because I'm putting it all on one tail. My z-score is still 1, but my probability value is sort of lower or sort of better than it was before because, again, I'm putting this all in one tail. So if I go through and I say, look at a z-score of 1, the value in the tail 1.5, 87, 1.59. I'm not splitting it. I'm not multiplying it by 2 because I'm putting all in one direction. Okay. So don't worry about this too much. We're not going to be doing a whole lot of one-tailed tests. We'll talk about this, why this is sort of down the road. But just knowing in terms of confidence bounds, if you're going to run one-tailed tests, what this does is you end up calculating not 95% confidence intervals, but 90% confidence intervals, and then just ignoring sort of the tail that's not relevant, that's not sort of something that you're interested in. All right. So we've gone through and done our tests. Then what we need to do is we need to draw a conclusion. What we want to do if we're doing good work and good critical work is we're going to draw some conclusion about the range of possible values, precision of my estimate, and the size of the effect based on my confidence intervals. What we're going to do is we go down through, we're eventually going to talk about effect sizes and integrate those into our interpretations. We're not there yet, but we'll get there eventually. Okay. So if I decide to reject the null hypotheses, this is the decision I would typically make when I have a test statistic that falls in my critical region. Okay. What this is saying is it suggests that my sample data are unlikely assuming the null hypotheses and all corresponding assumptions of the statistical model are true. Okay. Ali, why did I underline all corresponding assumptions of the statistical model?
I mean, just to like, sorry. I mean, because there are a lot of like other assumptions that are made.
Right. So if I say the Patriots win the Super Bowl, and we say this is the best team in football, right? Assuming that they've played by all the rules that everybody else is playing by and haven't violated those rules, right? If they have violated those rules, how confident are we that the Patriots are the best team in football? We start to lose confidence in that, right? Same thing with our statistical tests. Any Patriots fans out there? Awesome. I knew you guys were a good crew. Robert's got a scowl. I like that. Allie, are you a Seattle fan?
I don't really care that much.
Oh, okay. That's fine. Don't worry about it. As long as there's no stupid Patriots fans around here. Okay. So, but this is the thing, right? Like our statistical tests work as long as we're playing by the rules. As soon as we start violating assumptions, as soon as we don't have representative samples, as soon as our data don't meet the underlying statistical assumptions, as soon as our methods are all wonky or there's systematic bias, then all bets are off, right? But assuming that we've done that, assuming we've met all corresponding auxiliary assumptions of our test, if we're rejecting the null hypotheses, we're saying that these sample data are unlikely, assuming the null hypotheses. And what we do is we conclude that our sample was likely drawn from a population with some mean that's different than what was specified under the null hypothesis. Okay, so we use this as indirect support for our alternative hypotheses. We never really tested alternative hypotheses. All we're doing is we're focusing on the null. And what we're doing is we're saying, assuming the null is true, what's the likelihood of obtaining the data that we've got? If it looks if it's very different, what we would say is it looks like these data aren't compatible, or these data are very unlikely, assuming the null. And so as a consequence, it seems like these data were probably drawn from a population having a mean that's different than what we had assumed under the null hypothesis. People comfortable with this? Does it make some sense? This really needs to make some sense because we're going to get into some deep stuff in sort of the next section that will leave your ears smoking if not. Okay. So that's if we reject the null hypotheses. We also may fail to reject the null. This is a decision when our test statistic falls within the body of the distribution. We say that our sample data are plausible given the null, right? Our sample statistic wasn't exactly 80, but it was close enough for us to say null value seems reasonable based on the data that we've collected. Okay. But what we cannot do, what we can never do, is conclude that the null hypothesis is true. Okay. And again, people often talk about this as being an agnostic versus atheist approach, right? If I'm atheist, I say there is no God. God doesn't exist, right? God is sort of not there, right? If I'm agnostic, I say God might be there. I don't know. I just don't have enough evidence to sort of say one way or the other, right? Kind of like it's the same thing we're doing when we fail to reject. We're never saying that the difference is zero or that the population value is equal to sort of whatever the null value is. All we're saying is we just don't have evidence to say that it's not. So if you say there is no difference, I say, I don't know, maybe. I'm not saying I don't have enough evidence to say that there's not a difference, right? Or that there's no relationship or anything else. Okay, but never would we say that the null hypothesis, that these data provide evidence that suggests that the null hypothesis is true or that there's no difference or things. Okay, people comfortable with that language issue? All right, cool. So again, failure to reject doesn't prove that there is no effect. We see this all the time, right? I'll see in research saying like, well, we didn't have our p-value was too big, so there wasn't a significant effect, and so that these two groups aren't different. Nope, that's not what that says. It doesn't say they're the same, it just says that we don't have enough evidence to say that they're not the same. Okay? And the reason this is important, right? Let's say, Rachel, you're doing a study looking at differences in neuroticism against people who have a history of self-injury and people who don't, right? And let's say you've got a sample of 5 people who self-injure and 5 people who don't, and you run a test and you find that you don't find a significant difference. And you say that means that people who don't self-injure and do self-injure have equal levels of neuroticism, right? What's wrong with that conclusion?
You can't really claim that there's not an effect.
Uh-huh.
Or you just haven't found one necessarily.
Right.
With that sample.
And why didn't you find something with that sample?
Could be a lot of different reasons.
Yeah. But if you got...
Size, but
Yeah, but if from a statistical standpoint, if you're comparing a sample of 5 against another sample of 5, is that a good test?
No.
No, right? If I'm looking at samples of 5 and 5, I'm not going to find anything useful that you couldn't obviously see from a mile coming off, right? So again, what we have is type 2 errors, this failure to identify differences when difference exists because just don't have enough people and there's not enough error, right? There's lots of reasons why we don't find stuff. A lot of it's due to our methods, right? So we never say that 2 samples are. When we do this, we fall into. I'm not going to claim that I've never done this in a paper either. Sometimes gotten called out for it, right? Say like, there's no difference between these samples. Well, 1, the samples don't have the same number, so yeah, there is a difference. 2, we can't claim that there's no difference in the population because we don't have enough evidence to say that, right? So again, what you don't want to do, you hear about people complaining, well, you've hypothesized the null, right? My hypothesis is there's no difference between these 2 populations. Well, that's not something that we can usefully test with traditional statistical things because at best, I'm going to say I don't have enough evidence to say that they're not different, but I can't ever say that these 2 things are exactly the same. Okay. So again, failing to reject doesn't prove that there's no effect. It just means that we don't have enough evidence to say that there is. Okay. All right. Oh, yes, Wilkinson. Great paper. Never use the unfortunate phrase accept the null hypothesis. Like if I see in any assignment that you've accepted the null hypothesis, I'm going to circle it with a big thing and say, don't do that. All right. Oh, I have to. I think that was Tara that helped me with this. Oh no, you didn't. Okay, so we've gone through and done a bunch of stuff, but in terms of if we were just using plain Jane sort of basic null hypothesis testing for this first conclusion, this is probably what you've done in undergraduate statistics classes, is you just say, we found a significant effect. Or that our sample was significantly different than the null or something like that. That contains exactly 0 information that's useful for inferring anything helpful. Okay, if I find that something is statistically significant, all it means is that it looks like I have evidence of some non-zero value, right? Or some non-zero difference. What we need to be doing, and what some of these papers I'm having you read are talking about, starting to augment how we're talking and presenting about statistics in a way that furthers our understanding of the phenomena of interest, right? So for this scenario 1, if I were to go through and pull up and sort of talk about, put together an interpretation of what we found, I might say, point estimate of mean cognitive functioning in population of older adults taking antioxidant supplements, so I'm identifying my population, was 92. Data in this study suggests that scores ranging from 84.2 to 99.8, reasonable lower and upper bound estimates of functioning in the larger population. So I'm not just saying that it's different than 80 or that it's bigger than 80. I can say more than that. I've got data to say this is what I'm saying is sort of probably the score in the population of interest. The probability of randomly selecting a sample of 25 with an average functioning score of 92 or greater, assuming a true population value of 80, is 0.001. That's if I look at my Z table again. If I go and look at Z equal to 3. So the upper tail, so finding a sample with a score of 92 or higher is about 0.001. That's where I'm getting that. Okay. Test value falls in the critical region set by alpha 0.05, assuming no meaningful violations of assumptions of the underlying statistical model. Conventional decision rules recommend the rejection of the null hypothesis. Okay. I said a lot of stuff in there. What did I not say? What phrase isn't anywhere in that?
You accept.
Okay, that I accept it, so I'm not accepting anything. What else did I not do in there? Did I talk about anything being significant? Was anybody confused about what's going on in this? No, right? Like, my refusal to use statistical significance or a significant effect didn't confuse anybody. No one's sort of unsure about what we actually found. If anything, we've provided a considerable more information than what we typically see with sort of our interpretations, right? So again, in some of these papers that I'm having you read, in evidence-based sort of applied statistics, a big movement towards, again, not relying on the term statistical significance. Now, I'm going to say, that's not to say that, you could never do things, or if you do use the term statistical significance or say I have a significant effect, that it's bad, right? But we've already gone through and we've determined that no one has any problems identifying whether or not this value is greater or less than 0.05. And if it is, saying it's significant. If it's not, saying it's not, right? So what I'm going to challenge you to do, and what we're going to do for this semester, is try and sort of talk about statistics in a way that communicates information without falling back on calling things statistically significant or not. We're going to talk about why that starts to become problematic and why it leads to misleading stuff. Okay. So up here, giving sort of my interpretation of things, but then also wanting to think about sort of meaningful impact of our stuff, right? So here we say it's important to note, however, that estimates supported by these data are compatible with meaningful elevations in functioning relative to the general population of older adults, as well as lower bound estimates falling below the threshold for practical effects. Remember, at the beginning of this, we said, based on sort of work with this data, we're saying that anything that exceeds a difference of 10 points, that's something that's clinically meaningful. If it's not hitting 10 points, I mean, it might be different, but there's probably not anything that's worth getting worked up about in terms of a clinical perspective. So we would say, whereas these data offer support for higher assessment scores in older adults reporting at regular antioxidant use, additional data is needed to determine the extent to which elevations are consistent with meaningful effects. So what did I do in this second piece of things, which is something we typically don't see in our science? What do you think, Riley?
What is something you didn't do?
No, what am I doing with this second paragraph here?
I mean, you're condensing this stuff in the black.
Okay.
I don't know. I'm kind of confused on what you're asking.
Yeah. What are we adding in that second paragraph? Do we have evidence based on the data that the population of older adults taking supplements has a mean functioning score that's different than 80? Do we have data to support that?
Yes.
Yeah. Okay. So, Riley, remind me sort of what your research area is, sexual assault prevention stuff?
Yeah.
Okay. So let's say that I tell you that I have a program that improves or that increases or that reduces rates of sexual assault on campus that's different than 0. So it reduces sexual assault by some level that's not 0. Is that helpful for you?
Not really.
Not really, right? But that's what our statistical tests do. It says like, oh, yes, it reduces something, or it's a change, or it's a difference that's not 0. Rarely is not 0 something that's useful or meaningful to anybody doing any sort of practical work, right? What would you like to know about this program?
Like how much it's reducing.
How much it's reducing, right? And this is where sort of we start to go through. So we might find that a very elaborate and very unrealistic program that no one is ever going to use or adhere to reduces rates of sexual assault by 0.5%. Now, if we reduce sexual assault by any on campus, that's good, right? But in terms of something that's practical or useful or worth the cost or worth getting buy-in from people, I'm probably going to struggle with that, right? And so what we can do is we can start use our interval estimation to say, okay, this is about what we can expect this to reduce, right? So for here, so we're going beyond just saying that, yeah, supplements, based on the data that we have, supplements probably do have some effect on performance. What we're going to do is we're going to take sort of the estimates that we've got and compare it with what this clinical benchmark, right? So we say, well, on the high end, if the general population is 80, and on the high end we've got a value of about 100, that's about a 20-point increase, right? And that's pretty good. That definitely exceeds this level of change, right? But on the low end, we've got 84, and that's a 4-point difference, okay? And so if it's only a 4-point difference, yeah, maybe cognitive supplements sort of give me something on the margins, but is it anything that's interesting or useful for me if I'm working in this field? Probably not, right? Now, my point estimate was 92, right? And that's a 12-point difference, and that suggests that something could be going on. But overall, based on these data, can I say with any degree of certainty that I'm saying based on these data, I have evidence that, yes, supplements look to improve scores, but do I have evidence to say with any level of confidence that they improve scores to a meaningful level? Rather, you're shaking your head, no? No, right? Because my lower bound, so this is equally as plausible as this, right? So basically all I can say is it looks like, based on the data that I've collected, supplements either sort of notch it up a little bit or have a massive increase or somewhere in between, right? And if I'm wanting to know whether or not this has some sort of practical impact, I'm sort of left in an ambiguous situation, right? And so while I can say, based on the data, that my data suggests that, yes, older individuals who take supplements likely have a higher score than the general population of older adults, to the extent to which that's a meaningful increase, I don't know. Okay. And Robert, what do I do if I want to? So I've got a pretty wide confidence interval ranging from anywhere from something that an incremental increase to a massive increase. What can I do to start to increase the precision of that estimate?
Not entirely sure. Can you?
Yeah. What could I do to start to shrink that interval?
Appetize?
Yeah. What I can do is this might be, so do I want to pull in like 500 people to see if supplements work? That's probably not a good use of my time and resources, right? So maybe I do a small study first and I say, okay, it looks like I'm getting something promising. It looks like that these supplements are systematically associated with higher levels of functioning. Now, to the extent to which it's clinically relevant or not, I don't know, because my sort of interval is pretty big, right? But if I went through and I grabbed a sample of 100, Brittany, what's that going to do to my to my interval?
It's going to make it get smaller, so the
Yeah.
range will be smaller, right?
It's going to shrink it down, right? And so what I might get then, assuming that my point estimate of 92 is good, what I might see is I start to see that that interval estimate start to shrink down to something that gives me a little more precision, a little more confidence in sort of making a determination on whether or not yes, it's having some sort of impact. Is it an impact that's relevant or something that's going to be interesting for me for a practical standpoint? That's what we can start to talk about. Okay. Questions about sort of this. Okay. So this can be a hard thing to start to think about okay, how do I integrate all this information into some sort of summary or interpretation or something like that. I don't want you to use this as like a template and just and please don't cut and paste this and just swap out sort of things. But as we're going through these, I'm going to try and give you examples of how I might sort of put things together to start, so you can see how we might start to integrate information that we're getting from these tests in a way that conveys a lot of good information, good information and meaning that we can start to integrate into sort of interpretations. Okay. All right. Same thing here. Scenario 2. This is where we had a much smaller observed difference. Here we're going to say supplement use in older adults associated with an incremental increase in mean cognitive functioning. So it's sort of observed increase relative to scores from the general population. However, plausible estimates of functioning in the target population based on these data range from 76.2, 91.8. Probability of randomly selecting a sample with a mean cognitive functioning 84 or greater, assuming population value of n or 80 is about 0.159. And again, if we go to our z table and find a z value of 1 and see what's in this tail, that's going to give us this. So we say score falls outside the critical region set by alpha 0.05, assuming no gross violations and assumptions of the underlying statistical model. Conventional decision rules indicate failure to reject. Although these data are compatible with estimates suggesting meaningful elevations in functioning, right? So if the true population value for older adults is at the upper limit, the upper supported value of our data, 91.8, so it suggests that there could be something going on. The study is at best inconclusive with respect to the statistical and or practical benefits of supplement use. Okay? So again, we're just saying we don't know, right? Like at best, like what we've got, our data are inconclusive, right? We can't say whether or not supplements do help, whether or not they don't help. We don't know. Reasonable estimates go from, based on the data we've collected, are anything from a small decrease associated with supplement use to a fairly large increase. I don't know, right? This is not doesn't feel like a satisfying position to be in. But it's basically anytime we have a null effect, right, or fail to find evidence against the null, we just say, I don't know. So our data are inconclusive. There's not too much we can say. What we can say is that it's anywhere from a small decrease to a huge increase or a large increase, but our best guess is about a 4-point increase, but that's actually not clinically relevant. So it could be as high as about a 11-point increase or a 12-point increase. We just don't know, right? So being comfortable, I think, with recognizing that our data and our analyses are more often than not inconclusive and just kind of give us a who knows type of approach. It's important to sort of know that, recognize that, to make important interpretations. So, Robert, if you were to see this study, would you say, oh, there's no way I'm ever going to study the effects of supplement use in older adults?
Probably not.
Yeah, I would look at this and I'm like, well, I don't know. No joke, they didn't find anything. They only had a sample of 25. I might go through and look at their methods and see those aren't super great, right? And so just because they didn't find anything doesn't mean that I couldn't. But what I would want to do is take a look, critically evaluate that study before I decide sort of how to move forward with stuff. Okay. Questions. This is a little bit different than how we would typically, sort of how you probably classically were trained to interpret hypotheses tests, right? It's generally look at your p-value. Is it less than 0.05? Then you claim a significant effect and just be done with it, right? The problem is that doesn't give you anything useful for the level that you're at right now. What we're interested in is not only is there a difference or not, we want to know sort of what are the methods, what are the reasonable values based on my interval estimate, what can I draw from this, what can I infer, and how does this impact my sort of research or inferences about sort of stuff at hand. Okay. Questions about any of this?
When you're interpreting this, like we're looking at right now, are you basically saying that you can't like reject the null hypothesis because your mean falls within the values of the 76.2 and the 91.8?
Yeah. And this is Brittany, this is the mistake. This is the other thing that people will do too. And if you're reading these papers, they talk about this. What we don't want to do is take interval estimation and just say, is my null value in there? I mean, you can do that, right? And say, oh, null value falls in my interval, right? 80 falls between 76.2 and 91.8, and so that means I don't have a significant effect. Well, what I've done is I've just taken my interval estimate and just turned it back into a null hypothesis, and that's not a useful thing to do, right? What we want to be doing with this is saying, not just, is there a non-zero difference? We want to be saying, is it a practical difference? Is it a meaningful difference? Is it something that anybody should ever care about, right? Because what happens is sometimes we find differences that are trivially small, or a interval that's right up next to, right? My difference between my two groups isn't 0, but my lower bound estimate is a value of 0.01. Is that a meaningful thing that I should get excited about? Probably not, right?
Would you still say you failed to reject the null hypothesis then?
No, because using the rules of null hypothesis testing, I would say sort of basically my data is consistent with a possible possible difference in sort of whatever we're measuring across these two populations. However, lower bound estimate suggests a near null effect, the possibility of a near null effect. We need to go through and do some more research to see whether or not this is something that's going to be meaningful from a practical standpoint.
So when we interpret these, not saying, like, you want us to explain basically what it means exactly.
Yeah, because we're doing science, right? Like, that's what you always want to do. I can teach 5-year-old to identify something as bigger or less than 0.05 and say it's significant effect or not, right? That doesn't demonstrate that you actually know anything about it, so we're thinking carefully about it. But doing this, right, thinking about, okay, what are the upper and lower bounds, and sort of what does that mean? That's so you just start to think about things a lot easier. Now, to be fair, a lot of times knowing what's a practical or meaningful difference starts to get difficult, right? So we have to think carefully about that. But want you to be thinking more in this direction than just identifying things as there's a significant difference.
Mm-hmm. And when you're interpreting it, just to be sure, I know you said not to do this, but like, so I said 84, which is probably wrong. When you're looking at this, are you looking at your population mean, the U, and that's how you interpret it? Or are you looking at your... This is my reference value. This is the assumed value under the null.
Yeah.
Okay.
All right. Okay, I'm going to talk about a couple of types of error. Type 1 error. We make a type 1 error when I reject the null hypothesis when the null hypothesis is true. Okay, I'm basically saying that there's an effect there or a difference there when in fact there isn't one in the population. Okay, historically we've associated with this with the chance selection of an extreme sample. So like you'll hear people say, oh, the likelihood of randomly selecting a sample of size X with sort of a value that's sort of way different from the mean. Now, this is asterisk, and statisticians don't like this idea of talking about, like, oh, I randomly just selected a sample that interpreting your type 1 error as the probability of randomly selecting a sample is sort of at this level or greater. And that's because of all those auxiliary hypotheses. There's just so many reasons why you can get weird samples outside of just, hey, I just got super unlucky and pulled something that's away on the ends, right? So you want to be careful with that. But generally, when we're talking about type 1 errors, we're talking about saying that we have an effect when there is, in fact, not an effect to be had. Our alpha level set by you all, kind of, like, you can't say, I want my alpha level to be 0.2 because no one's going to like your study, right? Traditional levels, alpha 0.05. So we would reject when the probability of obtaining the data, assuming the null and all auxiliary hypotheses are true, is a 1 in 20% chance. So assuming that I have a perfect study with perfect methods and perfect measurement, and perfect randomly selected sample, I'm assuming that the sample that I've got, assuming that the null hypothesis is true, is going to happen 1 in 20 times. Okay, I could also set, so we can start to crank down the level. I set alpha 1.01. I'm going to reject the null hypothesis when I find the probability of obtaining the data, assuming the null and all auxiliary hypotheses is less than 1% or less than 1 in 100 chance of obtaining a sample this level or higher. Again, if we're thinking about that natural curve, right, and we're seeing this is my sampling distribution, if I've done everything correctly, only 1 in 100 times am I going to capture something sort of out here, a sample this extreme. And if I do, then fine, then I made a type 1 error. I'm saying that there's an effect here when there in fact isn't, because sort of 99% of the samples are going to come here in the body. I've gotten this one in the tail. But sort of the hitch on this is this piece, assuming the null and all auxiliary hypotheses are true. Okay, that's a pretty big assumption. So our thresholds for our type 1 error, again, if we're talking with our standard Z table, 1.96, this is associated with two-tailed tests of alpha 0.05, 2.58, this is alpha 0.01 on a two-tailed, 3.29, this is alpha 0.001, again on a two-tailed test. And when we're using Z tables, those are always going to be identical. We also have type 2 error. Type 2 error is going to be situations where I fail to reject the null when the null is actually false. Okay, I'm going to conclude that I don't have evidence for an effector association when in fact one actually exists. Okay, and what we see is these type 2 errors are associated with having insufficient power. Right, the power of my test or my experiment is my ability to identify an effect assuming one exists. Okay. We're most concerned about our type 2 error when we've got some treatment or manipulation that does have an effect. It's just pretty small and subtle. Okay, let's say, Erica, you're doing something with Ben and you're doing a lab-based study, and you've got a theory-driven, looking at a theory-driven mechanism where these individuals who get this manipulation should behave this way, which should be different than people who don't get the manipulation. And you're right. Your theory's right. Your manipulation works. It's just a really subtle effect, right? If you don't have a decent-sized sample, if your measurements aren't super clean, if you've got RAs who are kind of jumping around, kind of doing their own thing, not all of them are on track and running the protocol consistently, all of these are things that start to add fuzz and static in there. Your theory is good. Your study is good. Everything's working. You just don't have enough signal there to detect it because you lack power. And so if you fail to reject the null hypotheses, you've then made a type 2 error here. This type 2 error is what we do more often than not, and we'll get into some of the problems with sort of the logic around this in the last section. Okay, so again, if you want to put this in a table, if there is an effect, the null hypothesis is true, and I reject the null hypothesis, I say that there is an effect when there actually, in fact, isn't one. I've made a type 1 error. If an effect exists, the null hypothesis is false, and I fail to reject, I say that there's nothing there, that's when I made a type 2 error. But if I reject the null and an effect exists, then I made a correct decision. If I fail to reject and there's no and the null is true, there's no effect, I'm correct, but here's where I make my errors. Okay. And so in general, in psychology, our stuff is always underpowered. We rarely have sufficiently powered studies, but one of the other things that we need to also be thinking about are overpowered studies. Okay, I'm working with on Tuesday. I was down in Boulder working with getting oriented to working with like census level data, where you've got millions of observations. Right, if I grab any two variables and I test whether or not there's an association with two completely unrelated things, am I going to find a correlation of exactly 0? Now, it's all going to be like 0.003 or something like that, right? But if I've got that many people, my p-value is going to be wicked small because it's going to say it's not exactly 0, right? And so what we want to watch out for is with really, really big samples, people saying, oh, there's a difference between these two groups, or oh, there's an association. Well, if I've got a correlation of 0.02 is not 0, But does anybody care about a correlation of 0.02? Nope, right? Or I find a difference in sort of weight of across this group or that group of 1/10 of a pound. Does anybody care about that? Nope. If I get a big enough sample, I'll detect it. It just doesn't mean that it's impactful or important, right? And so this is where we start to get important. And sort of one of the things that we've done wrong in our approach to science is we've given this label of significant, which makes it seem like it's important, when in fact all that means is that our data suggests that the difference between these two groups isn't absolutely zero, or the correlation isn't absolutely zero, right? And so this is where, with some of the interval estimates, some of the stuff that's being pushed in the papers I'm having you read, starting to divorce some of that stuff. All right, cool. Let's take a break. Let's come back at 4:25, and we'll sort of move through the rest of this stuff, try and get this knocked out. Okay? All right. All right, folks. How are we feeling about estimates, interpretation, so does this very, very basic, simple null hypothesis testing stuff? Feeling okay with this? Okay. We've spent a little bit more time on this, but I think this is good because this is going to serve as the basis for everything that we're doing moving forward. So again, placing a focus not just on identifying, like, do we have evidence of a difference or not, but then getting into point estimation stuff, and then sort of interval estimation, and thinking about practical implications of some of the stuff that we're doing. Okay. So, this. Okay. So we're going to finish up talking about criticisms of null hypothesis testing. Okay. Null hypothesis testing sort of really started to develop beginning of the 20th century and has been lambasted from the very beginning. Okay. And some really colorful ways of methodologists expressing displeasure or concerns with what's going on. This Meal paper basically talk about null hypotheses as a ne'er-do-well, right? Sort of going through, seeming like it's doing a lot of stuff, but actually not doing much at all, right? And maybe actually even holding our science back. Cohen, this naked emperor, has been shamelessly running around for a long time, right? Like, we've got something with major, major flaws that everybody knows is flawed, but no one wants to do anything about it, right? There's now wide agreement among statisticians who have studied the issue that reporting statistical tests using p-values is illogical and inappropriate. Identifying things as significant and non-significant. Strongly discouraged from continuing this never justified practice that was sort of developed out of sort of confusion. Okay, Wasserstein saying, we conclude that it's time to stop using the term statistically significant entirely, nor should variances significantly different, non-significant survive, right? Whether expressed by words, asterisks, or some other way. Okay, so people who do this, like people who study this, right? What we would talk about is evidence-based science. People are saying, like, our system is broken, right? And so the reason they're going through is, despite clear criticisms, we continue to do things the same way, right? But what ends up happening, sort of wanting to understand sort of what exactly do people find objectionable about null hypothesis testing. And what it turns out is there's some methodological, conceptual grounds both that really make the whole system shaky at best. Okay. So first criticism is our fundamental logic. So our question as scientists is, what we want to know is, given the data that we've collected, what's the probability that the null hypothesis is true? Okay. I've collected these data. Based on the data that I'm seeing, how likely is it that the null hypothesis is accurate, right? That's what we want to know. But with null hypothesis testing, with our hypothesis test, the question that we're actually asking is, assuming that the null hypothesis is true, given that the null is true, what's the probability of the data? Okay. Now the problem is is this logic works out under certain circumstances. If I say, if the null hypothesis is true, these data cannot occur. If I say these data have occurred, therefore the null hypothesis is false. This is a fine logical argument, and it works. Okay? But what we do, instead of saying, if the null hypothesis is true, these data cannot occur, we take that and we tweak it. And it seems not to be a big deal. We say, if the null hypothesis is true, these data are unlikely to occur, right? For our supplement example, we say if the null hypothesis, if the mean functioning score in the population is 80, it would be unlikely for these data to occur, right? And we would say these data have occurred, therefore it's unlikely, the null is unlikely to be true. This seems like a reasonable sort of logical progression, right? But as we start to fit things in, we start to see that this is problematic, right? So let's take this and actually give an example, right? If a person is an American, he or she is unlikely to be a member of Congress. This person is a member of Congress, therefore he or she is unlikely to be American, right? This seems good. This is sound. This is consistent. This seems like it should work, but when we actually start plugging things in, we start to see problems with the fundamental logic of things. Anybody here take philosophy courses? Done any sort of... Okay, some folks. So this starts to get into some philosophy, sort of fundamental logic arguments, where it seems like we make sort of small adjustments, but when we do it, things start to break down very quickly. Okay, and this right here is what Cohen refers to as the illusion of obtaining improbability. Right? Again, the problem is the question we're asking with our hypothesis tests isn't the question that we're actually interested in asking. It's a flip of it, but when we flip it, things start to fall apart. Okay. We also criticized with people pointing out that these, the question that we want to ask and the question that we are asking, probabilities associated with these are not the same thing, right? So what, again, the scientific question that I'm interested in is what's the probability of the null hypothesis? What's the probability the null hypothesis is true given the data, right? And if we put this in logic format, we say, what's the probability of the null given the data? But when we ask with our tests, it's what's the probability of the data given that the null is true? So what's the probability that the data are true, or what's the probability of these data assuming the null hypothesis, right? These are not interchangeable, these are not inverse probabilities. They don't go back and forth, okay? So we could say, again, the probability that you speak English if you attend this class versus the probability you attend this class if you speak English, right? These are two very, very different probabilities. We're just flipping it around, but we're getting wildly different and non-equivalent probabilities with this stuff, okay? So what we do is we want to, with the whole null hypothesis testing approach, what we want to do is we want to reject the null to conclude that the null is unlikely, okay? But mathematically, this starts to get very, very complicated, because if I want to calculate the probability or the likelihood of the null given the data, what I need to know is the probability of the null before I collect the experiment, right? Has anybody done anything or been exposed to any type of Bayesian types of analyses? We'll talk about it a little bit, but sort of the idea is, if I really want to look at the probability of the null based on the data, what I have to do is, before I run anything, I have to have some estimate of the probability of the null before we even start, okay? And this is problematic because we rarely, if ever, have some good, accurate estimate of the null hypothesis. Okay? So I pulled this from one of the papers that you pulled in, but we're going to go through and talk about just as a numerical example to try and sort of give this some feel, okay? So if I go through and I take a look at base rates of schizophrenia in the population, this is a very rare occurrence, right? We'll say it's 2%. So if I looked at everybody in the US, I would expect about 2% of the population to have schizophrenia. That's probably high, but let's say that's what it is, okay? And so I've got a screening measure. So I've got a measure to test for schizophrenia that demonstrates 95% accuracy for positive diagnoses, right? So this is, if I've got a positive test, or for individuals who have schizophrenia, the likelihood of a positive test, 95%, right? So if you have schizophrenia, 95% of the time I'm going to catch you, right? It's also 97% accurate for negative diagnoses. So this is a specificity issue. So if you don't have schizophrenia, 97% of the time, I'm going to detect your test is going to come back negative for schizophrenia, okay? How are people feeling about this screening measure? Brittany likes it. Anybody else like it? Yeah, you should. This is incredible properties of a measure, right? And so if we go through and we do a little bit of notation. So here, our null HO, this is the case is normal. You don't have schizophrenia. H1, the case has schizophrenia. T, this is our positive or negative test. And our sensitivity, the probability of a positive test given a case of schizophrenia, 95%. Probability of a negative test given a non-case is 97%. This is really good, right? The problem is, so again, the probability of a positive test given a non-case is 0.05, right? So if we take 0.1, all the cases, pi minus 0.095. And so what we would say is the probability of a positive test given a normal case is only 5%. And so from a null hypothesis standpoint, we would conclude that this is very unlikely. And we would say if you have a positive test, we're going to say that you have schizophrenia, right? Because the likelihood of a positive test for people who don't have schizophrenia is very unlikely. Okay, people following me up to this point? The problem is this doesn't address the question of interest. The probability of diagnosis given a negative, or probability of the data given the null, assuming the null hypothesis is not the actual, doesn't equal the probability of the null hypothesis given the data. Again, we talked about this. These two things aren't interchangeable. Okay, and if we actually start to work this out, if we look at the actual probability of a normal case given a positive test, so what's the likelihood? What's the probability of normal case given a positive test on my screener? We actually need to calculate this as the probability of the null times the probability of a positive test given a non-case over the probability of the null, or the probability of non-diagnosis, times the probability of a positive test given a null case plus the probability of a diagnosis times the probability of a positive test given a positive case. Okay, so mathematically, the question we're actually interested in is pretty complex. And if we actually run this out, the probability of a non-case given a positive test actually comes out to be not very rare. It's actually quite common. Okay, about 60%. And if we go through and we take a look and sort of take this and kind of map this on, right? So here we have individuals, we have 979 individuals who are non-cases, and we have 21 people who are cases, okay? So again, this gives us about a 2% prevalence of schizophrenia in, let's say, this population of 100, right? Well, if I go through and I take, for normal individuals, if I say only 30 tests out of 979, right? Or excuse me, 30 tests out of 979 total, that's going to be very high probability, or a negative test given a normal case is going to give you about 95%, right? A negative test given a positive case is going to be about 97%. But if we look at the probability of a positive test in a normal case, right? If we take 30 divided by 50, we get about 0.6, right? And so again, what we've done here is we're saying the probability of a positive test given a non-case is very rare. But this is a different probability than the probability of a normal case given a positive test. This is very rare. This is very likely. All we've done is just switch this around, but it's not the same thing, right? So the concern is because we do this all the time, we're saying that the likelihood of obtaining the data that we've got, assuming the null hypothesis is true, is very unlikely. And so therefore we're saying that the null hypothesis is sort of unlikely to be true. But that's not the question that we want to ask. We want to ask, given the data, what's the probability of the null hypothesis? And that can be a very, very different number. Okay. Now, anybody for 1 billion points, why is this working out this way? Why are we getting such a discrepancy between probability of a positive test given the null hypothesis, or the probability of a positive test given a non-case versus the probability of a non-case given a positive test? What's causing the discrepancy here? It's a base rate. Okay, base rate here of schizophrenia is about 2%. We're trying to detect something that's very, very rare, right? And in this case, right, like, let's say, Brittany, like, if I'm going to go through and I'm going to put together a screener for an active shooter, right? What's the best way to get a really good test to identify active shooters?
I'm so sorry. Can you ask me again? My contact is like giving me fits, and I was going to take it out. What?
Okay, never mind. Go take it out. Go take it out. I'll bother somebody else. All right.
I'm so sorry.
No problem. Allie, what's a good way to identify? What's a good way to get a really, really accurate screener to predict who's going to be an active shooter?
Like, I don't know. I'm confused.
Yeah.
Like, just asking, or
Yeah, if I ask.
like, that would be.
Yeah. What about if I just identify, so everybody takes my screener and I identify no one as an active shooter? How good is my test going to be? Really? How many in my sample of, let's say, 1,000 people, how many active shooters am I going to have in that group?
Not a lot.
Probably 0, right?
Yeah.
Even if I have 1 in there. If I go through and I say everybody's not an active shooter, I'm right 99.9% of the time, right? And so this is what starts to become problematic. If we're trying to identify something that's very rare, we start to see sort of discrepancies in these probabilities, right? So this is just an example that Cohen goes through, but does it very well, showing that the probability of the null given the data and the probability of the data given the null are not equivalent. They're not the same thing. And so basically everything that we're using to determine the likelihood of, we're answering a question that's not the question that we're actually asking, essentially, is the argument against this. So, another argument, I think this is one of the more compelling arguments. Criticism of the null hypothesis testing is the null hypothesis is always false, right? It can only be true in the bowels of a computer running a Monte Carlo study, and even if a stray electron may make it false. So if the null hypothesis is always false, what's the big deal about rejecting it, right? Is the average extroversion score in group 1, group 2, and population 1 and population 2, is it ever going to be exactly the same? No. There's always going to be some difference, right? RA is the average spatial reasoning score in one population of individuals and another population of individuals. Is it ever going to be identical, the exact same? No, right? And so if the null hypothesis, if there's always going to be a difference, if no two populations are ever going to be identical to 1,000 decimal places, who cares if they're not, if they're different? Who cares if there's a non-zero difference between these populations? And so Tukey's saying it's foolish to ask if the effects of A and B are different because they're always different to some decimal place, right? But our whole system is based on determining, is there a non-zero difference? Well, there's always a non-zero difference. From a theoretical standpoint, it's never going to be identical. So why do we care? I like this Thompson quote. Statistical significance testing can involve a tautological logic in which tired researchers, having collected data on hundreds of subjects, then conduct a statistical test to evaluate whether there were a lot of subjects which the researchers already know because they've collected the data and are tired. Again, Rachel nodded her head. If I've got a sample of 10,000, am I going to find a statistically significant effect for anything that I look at? Absolutely. All the test tells me if I got a lot of people. Doesn't tell me anything useful, right? Now I start to get very precise estimates about what that association is, and that can be good, right? But the whole sort of system is organized towards identifying whether there's a non-zero difference. And whether or not there's a non-zero difference is not an interesting question because there's always going to be a non-zero difference. So again, Meal talks about this a little bit. Regardless of the theory, rejection of the null hypothesis expected in prediction half of the time, right? I can come up with whatever nonsense theory that I want, right? And if there's always going to be a difference, if group A and group B are never identical, just at random, half the time B is going to be bigger than A, half the time A is going to be bigger than B. And so as the problem is that even if I have a completely irrelevant theory that has nothing to do with actual real life, at a theoretical level, I'm going to get results that support my unreasonable theory at least half the time as my power starts to increase, right? If A and B are functionally unrelated in any sort of meaningful way, right? At least half the time, B is going to be bigger than A is going to be bigger than B as I start to get sort of super fine distinctions, right? So asking the question, is A different than B, is nonsensical because A is always different than B to some degree, okay? And I'm going to start to find the probability of me finding support for my theory starts to increase quite a bit the more that my nonsensical theory aligns with a reasonable theory that actually just happens to predict things in the same way, right? I can have a theory that says space aliens cause PTSD for people as trauma gets more and more severe, the space aliens get more and more angry, which they inflict PTSD on people sort of more and more, right? Turns out, you know what? I've got a whole lot of goddamn research that supports my space alien theory, right? The problem is I've got a nonsensical theory that just happens to map on predictions in the right direction. And so what we start to do is use this as a really, really rough tool for things that don't actually support sort of the specifics of my theory. We also get this crud factor, right? This is Meal kind of coined this. Everything is related to everything else. Like if I get a big enough sample, something will be, the correlation is never going to be zero. It's never going to be exactly zero. And if I've got a big enough sample, I'm going to get a significant effect for that. So who cares about significance? Why are we spending all this time talking about it if the null hypothesis is always false? Yeah. Also, we alluded to this. The null hypothesis isn't interesting, right? It's hard to think about a situation where any non-zero difference is going to be scientifically or practically or theoretically meaningful. I can't think of it doesn't matter how infinitely small the difference is as long as there's a difference that makes me happy or is meaningful in some degree, right? When we're doing our hypotheses testing, almost always when we reject the null hypothesis, when we find a significant effect, it just means that A is not equal to B, or that the association isn't exactly zero. This isn't interesting or meaningful, okay? Let's say I've found an experimental manipulation that results in 1/20th of a standard deviation increase in outcome. All right, it's not zero, but is 1/20th of a standard deviation anything that's interesting from any sort of practical standpoint? Probably not, right? Maybe, but then it's up to you to tell me why this is important or why this is meaningful, okay? Intervention produces a change in self-reported symptoms that's not zero, right? If I'm a clinical person, back, hey, Allie, you're coming in, we're going to do treatment. I'm back, hey, I've got a treatment and it will treat your symptoms by something that's not zero. How excited are you about your treatment here? Not super excited, right? Yeah, they go back, oh, I get to improve by something that's not zero, okay? It's not useful, right? I've got a multi-million-dollar air quality initiative that reduces pollutants by 0.5 parts per million, right? I don't know. Seems like not something that's useful or worth spending multi-million dollars on, okay? And so this is the problem, and we talked about this a little bit before. Our hypotheses tests don't explicitly address precision or magnitude, right? And when we start getting hyper-focused on whether or not we have statistical significance, we start to overlook whether or not there's any sort of practical meaning or influence of sort of what we've done, right? We just say, yeah, it's not zero, but we're not looking at that upper lower bound. We're not considering precision of our estimate, right? It could be anywhere. Your reductions in my treatment could be anywhere from 1/10 of a point to 50 points. I'm not super excited about that treatment because it's anywhere from nothing useful to massive improvements. Now, it's not zero, so I'm going to say I have a significant effect, but what that actually looks like from a practical standpoint starts to become very, very ambiguous, right? Quote from Holbert, the statistical use of the word significant will never be understood by those without statistical training to mean anything less than its synonymous important and influential, than its synonyms important and influential, right? And so we start to get confusion in terms of what these results mean. We also see that these dichotomous decisions, these significant, not significant, or reject, fail to reject, terrible indicator of replication. Okay, so this is from a Cumming and Fitch text. We've got a pair of studies evaluated the efficacy of a new intervention for insomnia. Based on a sample of 44, Lucky 2012 noted statistically significant advantage of intervention relative to weight lift controls. No Luck failed to observe a statistically significant effect in a similar sample of 36 patients. Okay, so we've got one study that found a significant effect, one study that found a not significant effect. Rachel, what do you conclude based on these this pair of studies?
You're not really sure.
Then I'm not really sure, right? If all I know is that one study found a significant effect, the other one doesn't, sounds like they're pretty conflicting, right? But if we start to look closer and we say, do these pair of studies provide consistent or inconsistent information, or what types of conclusions can we draw? If we start to map this out, Rachel, as you're looking here, are these studies more similar to one another or less similar to one another?
They look more similar.
Yeah,
to one another.
if we actually look closely, it looks like we've got one study with slightly more people and a slightly narrow confidence bound. Doesn't contain zero, right? So no change or no difference than wait list is not a reasonable estimate for my first study. Here, I've got a slightly smaller sample. And is zero plausible? Is a zero difference plausible for my second study, Rachel?
No.
For my second study, the red one.
Sorry.
Yeah,
Yeah.
it is, right? But that confidence interval is just catching that bottom bounds of it, right? It's just barely tipping over to zero, right? Lower bound estimate here says I might get an improvement of 1.5 points. Here, I'm saying I've got a worsening of about 1/3 of a point, right? But this second interval just barely catches zero, right? And if we look, there's far more overlap with these two studies in terms of their estimate for benefit as opposed to the difference, right? But if all we're focusing on is whether or not there's a statistically significant effect, we miss the fact that these two studies actually are telling us a lot of the same stuff, right? Based on these data, giving a careful evaluation, I would say actually looks like this intervention might be beneficial, right? I might sort of want to continue to take a look at it as opposed to just offhandedly saying that results are conflicting here. But if all we're looking at is sort of did I find an effect or not find an effect, I'm missing all of that stuff. Yeah. Again, if I go through and take a look at sort of my effect sizes here, mean difference right? Effect size, this is found, my point estimate is about a half a standard deviation increase. This is about a third of a standard deviation increase. My effect sizes aren't really all that different. They're both kind of falling in this same level, right? This would definitely say, if we start to take a closer look, looking at our interval estimates and our effect sizes, we start to see, well, there's actually maybe something more here than would be on the face of just identifying things as significant and not. All right, we also get bias against the null, right? We tend to associate theoretical predictions with rejection of the null, right? The problem is if we start to monetize rejection of the null hypothesis, and you experimental folks have sort of had more of or sort of put more of a focus on this in terms of replication crisis stuff, right? We've basically incentivized researchers to reject the null in order to publish and sort of support your theory, right? But what ends up happening is if I've got a bunch of studies who have tried to do something and 90% of them haven't found anything, and 1% of them, and 1% of, and one of them has, what's the one that gets published? The one that found it, right? And the 90 that didn't find it, those didn't get published, right? So now all of a sudden we think this is a thing when in fact it's not, because there's been multiple failures to replicate. We also see this when people talk about this in terms of p-hacking, right? I ran 50 different analyses. One of them worked, just probably by chance, and so that's the one I sort of go through and report, right? And so what we see here as a consequence of this are effect sizes based on the literature almost certainly wildly overestimating the true effect sizes that we should expect in the population, okay? So when I'm doing a power analysis, if I'm going through and I'm finding published studies to try and get an estimate of effect so I can power my study, that effect that I've pulled is probably a wild overestimate of the actual effect that I'm looking for, right? Because Erica's looking at the relationship between X and Y, and she finds two studies, right? And she finds a correlation, say, oh, it's about 0.5. But what we don't know is all the studies that have tried to find this and actually have not found an effect. The effect is actually more closer to 0.1. And if I've got an effect size of 0.1, how many people do I need to reliably detect that effect? Lots, right? Probably more than those people had. And so they failed to reject the null hypothesis. So no one ever sees those. The one study that had really weird results or maybe questionable methods found this effect. And I'm trying to power my study for an effect size of 0.5, when in fact the actual effect in the population is at best 0.1. And so what happens, what's the likelihood of me detecting that effect if I'm powering for an effect of 0.5 when in fact the effect is 0.1? Am I going to detect my effect? Nope, not unless I get a really weird thing that falls way out of bounds, right? And so what we see is just because based on this publication bias, those studies, those strange studies or studies that have questionable methods that end up sort of catching an effect size way on the end of the distribution or find a difference that's not close to being representative of what is actually reflective in the population, that's the stuff that get published, and then that's what our science gets built on, right? Again, this hasn't hit clinical folks to the level it has experimental folks, but no one should be shocked that this happened. People were really up in arms about this failure to replicate anything. If you understand sort of anything sort of basic about how these statistics work, you're like, absolutely. If this is the way we've built our system, of course this is what's going to happen, right? So, Cohen's talking about the result is that people who do focus on effect sizes end up with substantial positive bias in their effect size estimation. Furthermore, there's the irony of sophisticates who use procedures to adjust their alpha for multiple tests and are adjusting for a non-existent alpha error, thus reducing their power, and if lucky enough to get a significant effect, only end up grossly overestimating the population effect size. Okay, this starts to get into this area, right? We not unreasonably, but we get sort of worked up about multiple tests and alpha inflation. But in general, what are we more likely to make type 1 errors or type 2 errors?
And you say 2 is
Yeah. Because we're always underpowered, right? The types of effects we're looking for in psychological science are almost always small and subtle. And we don't have enough people to detect those effects. If we do detect an effect with a small effect size, if we do detect an effect with a small effect size in a small sample, it's probably something that wildly overestimates the population estimate. But then that's what gets published, and then everybody thinks the effect size is R equals 0.4, when in fact the population effect is R equals 0.1. But everybody's chasing R equal 0.4 because that's the only thing that's been published. All the stuff that doesn't publish gets sort of put away in a file drawer. And so then we've got big confusion. And if I'm starting to sort of tack on, so I'm going to say, I'm going to make my alpha level 0.0001, I'm just increasing the likelihood that the only thing I'm going to find is something that's a gross overestimation of the actual effect in the population, perpetuating this further along. Okay. So again, our system is set up for reasons, but the problem is there's consequences to the way we've set things up, particularly if we're not thinking clearly about what our tests are doing and how they're getting put together with things. All right, cool. Let's stop there because I don't want to. We're close to being done, but I don't want to take it too far over. We'll finish up with the last couple of slides next Wednesday and then jump into t-test stuff. Questions about anything that we've covered up to this point, where we're at, where we're going, or anything like that? Okay, cool. So what this means in terms of thinking about your time and effort and stuff, we would supposed to have our test or our problem set for hypothesis testing stuff. So this would be problem set 3. Would technically be due next Friday based on the syllabus. We're not technically through this lecture material yet, so we'll push that back. Okay, so if I'm looking at my calendar, we would normally have had problem set 3 due on the 2nd. We'll have that due the 9th instead. Does that sound good? Okay. Good deal. All right. How are people feeling? Head spinning a little bit with this? Yeah. It's kind of some philosophy, sort of logic types of stuff that can be a little bit tricky to wrap your head around. We'll keep going over it. We're going to keep talking about this stuff. But if you have questions or you're trying to work through things, let me know. If you have questions about this assignment, reach out, get in touch with me. Again, if you haven't jumped into it, sort of do it soon. There are aspects of these assignments that are, these first couple ones are pretty straightforward. They'll get more labor intensive as we move forward, but please don't underestimate the amount of time that it'll take you to put together good, thoughtful responses. Again, you guys did a nice job with the first one. Just make sure that you're giving yourself enough time, reaching out ahead of time before kind of last minute stuff. Okay. All right.
I'm going to post problem set 3 because last time you were like, you're going to post it and you're like, you should have emailed me if you want it and I will email you.
Okay, good. Yeah, do that. Right. This is the thing. I'm a terrible judge of knowing what you all care about. Right. In my head, I'm like, this is a thing that probably everybody's thinking about, and you're not, because you could care less about what I'm talking about. And I understand it doesn't offend me at all. So if I don't hear from you from anything, I'm like, okay, well, I'm sort of doing other things. I guess no one's interested in taking a look. But yes, I will go through, get that problem set posted so you can get on, get an early start. Right now, let's focus on 2. Make sure you're working on that. But if I drop the ball again, if I sort of my compensatory strategies for remembering things fail, always say, hey, Bozo, you said you were going to post that. Please get that up so we can get on there. Sound good? Cool. All right. Other questions? Okay, cool. You guys are awesome. Thanks for hanging in there. Let me know if you're running any questions. Otherwise, we'll catch you on Wednesday. All right. We'll see you.